Hello everyone, and welcome to your math lesson today with Everyday Seminar. Before we begin, let's go through the solution to last week's problem. Okay, so the question was, what is the integral of 2x plus 5 cubed in relative to x? First thing we do is we expand. Okay. So 2x plus 5 multiplied by 2x plus 5 multiplied by 2x plus 5. So that times that, okay? And once you do all this, you get to 8x to the power of 3 plus 60x squared, or to the power of 2, plus 150x plus 125 in respect to x. Now, what we do here is, don't forget our formula, xn plus 1 over n plus 1. Okay, that's our key formula right there. So what we do now is xn plus 1, so 3 plus 1 equals 4, so it becomes x to the power of 4, keep that there, over n plus 1. n plus 1 is 4, so 4 plus 60x plus 1, so it becomes 3 now, over 3, plus that term, that's 1 term, 2, 3, 4. The next one, 150x, add 1, so now it's, instead of 1, it's 2 now, x to the power of 2, over n plus 1 over 2, plus, we have here 125. So here there's an invisible x0. Okay, here it's 125x0, which this x0 equals to 1, right? So now we're going to add 1 to 0. It's going to become x1 over 1, okay, over x. And now we can just cancel here. That becomes 2x to the power of 4. That becomes 20x cubed. 150 divided by 2, that's 75x squared, plus 125x, plus c. Don't forget to add the c at the end, the constant. Okay, because this c can be plus 100, plus 200, plus 3, plus 4. So that acts as a placeholder for any number, and that's our answer there. Okay, let's move on. Okay, so our topic before, we were on integration, also known as integral calculus, and before we did the indefinite integral. Okay, now we're going to be doing the definite integral. And it might be slightly harder than before, but you'll learn a lot. Let's move on. And our key terms for today: integration, the definite integral, the x-axis or the horizontal axis, that's the x, the y-axis or the vertical axis, okay, y, rectangles and approximation. And as a bonus, I've included a picture of Isaac Newton and Gottfried Leibniz. Okay, so the definite integral. Here's an example we have there, that function right there. Now that is read as the integral from a to b of fx dx, or the integral, okay, that means the integral from a to b of the function x with respect to x, dx with respect, or in relation, with respect, in other words, in relation. Again, notice a and b are boundaries or limits. So a is the lower limit and b is the upper limit. So that can be, for example, 3, and that'll be 6 on the x-axis. Okay, imagine the x-axis. So we're probably talking about an area from 6 to 3, and that area there. This is the upper limit, b, on top, and the lower number goes on the bottom, a. What else? Also note that the variable x is a dummy variable. So instead of x, we can have t, or we can even have v, f or v, or any letter. Okay, r, for example. Okay, let's move on. So let's look at the definite integral as a total. Okay, let's look at it in another way. Look at this example. If at time t minutes you are traveling at a rate of v bracket t feet per minute, or that's a rate, a function of speed, then the total distance traveled in feet from minute 2 to minute 10 is given by the total change in distance from the integral of vt in respect to time from 2 minutes to 10 minutes. And here's something else, another way to look at it. Try imagining a graph with time on the x-axis, time, and speed on the y-axis. So let me just do that again. That's y, and we have speed, and here on the x-axis we have time. Notice that the area of the curve is equivalent to the values from the x-axis multiplied the values on the y-axis. So distance equals to speed times time. Now imagine we have 2, 4, 6, 8, 10. That's 10, 8, 6, 4, 2. So say we have a graph like that, going like that, and we want to know how far did this person go between 2 minutes, and 10 minutes. So the definite integral shows this. Okay? When you evaluate this function or this integral, you get the value for the area in there. So it's basically, you get, which is the distance traveled, the area, which equals to that speed multiplied by time. And this is different from what we talked about before, the differentiation. Okay, the one with that sign, or dy over dx. This differentiation, or differential calculus, is a rate. Okay, that divided by that, it's a gradient of the line. So that's what makes it different from integration. Okay, let's move forward. Another example, the area problem. Find the area of the following region. A rectangle, okay, or a square, the area is the length times the width. Triangle, the area, okay, area. The area is half the base times the height. That's the formula. Another example, how do you find the area of this? The area would be A1 plus A2, plus A3 plus A4. That'll give you the whole area. Now, the definite integral of the left diagram would be written as, this is similar to what we just did in the slide before. We'll write the integral from A to B. And this is a function y equals to fx of y equals fx with respect to x. It'll be written like that. And the answer to this will be this area. You'll get S, okay, which is an area. Area below the line. Or under, area under the line. Or under the graph. Okay, more on this. Let's move on. So how did all of this come along? Integration, the definite integral. It started with a problem, the area under a curve. So this was a very old problem. A lot of mathematicians were trying to solve it. What's the area below the curve, under the line? Okay. Now the idea from Riemann, the idea was we will introduce triangles under the curve, many triangles under this function, the function of x. And we find the area, say we want to know from here to here, okay, we want to know the area of all this. So what we do is we put rectangles underneath, and then we know how to calculate the area for a rectangle, right? It's the length times the width, I guess we use. or here multiplied by here. So we'll find the area to that, plus that, plus that, plus that, and all that will give us an approximation of the area here. Approximate, okay? Approximate answer or an estimate. But it will never be exact because you still have these small spaces here that we're not including. So what do? First of all, let's move on. So in this example here, we take the left points of rectangles. Okay, we put them under a curve. And this is the function here, or the curve is basically y equals x squared. So we want to know what's the area from 0 to 1. Okay. Now here we use n equals 10, which means equals the number of rectangles. So when we use 10 rectangles, we find the area of the rectangles, we get 0.285. Now, if we use smaller rectangles, you see these spaces here, they become smaller. So this is better than that. Okay, this estimation, this approximation is much better than this one. So as you see, the new area now we have with 30 rectangles, this 30 is 0.3169. Now, if you do 50 rectangles, these smaller gaps become so small that this is a better estimate than this one. So here, using 50 rectangles, we find out that the area under the curve from 0 to 1 is 0.3234. Okay, let's move on. Now, have a look here. Here is where we use the right points of the rectangles. Okay, same thing, here's 10 rectangles, 30 and 50. Notice now that these rectangles, if we count the areas of them, they go above the function, above the line of y equals x. So this will be larger than the real area below the curve. Okay, this one will be much larger. Too much. And here's with 50 rectangles. Again, you see that there's still space. It's still going over the line. So, shall we? What we then notice is that if you take the left points and you're increasing, there's an underestimation because you have space. But as the curve goes down or decreasing, it's overestimation. Your guess or your estimate, your approximation is too high. Taking the right endpoints of triangles, as it increases, you have an overestimation. And you see how it's going over the actual line? You only want this area. And as the function is decreasing, you have an underestimation. You're not including these areas. Now, if you take the midpoints of the rectangles, okay, the midpoints, it becomes closer and closer. See how that those extra spaces are much smaller? Now, what does this mean? So here's a summary. The great Riemann, mathematician, the problem area under a curve. Let the change in x equals x1 take away x0. This is the base of the area, okay, as we spoke about. That'll be the change in x, x1, x0. I'll just briefly go over this. This is the base of the area. As the change in x gets smaller, different rectangles. We're talking about the rectangles here. As the rectangles get smaller, the smaller and smaller. The approximation for the area under the curve becomes more accurate. Bernard Riemann thought of an idea using the concept of adding small rectangles. This is his formula. What it shows here is we have a limit as the number of rectangles approaches infinity. So if we have a curve like that, 3 rectangles, and we find the area, it's not as good as having unlimited rectangles. And the smaller they are, the closer your answer will be, the better it will be. Just briefly on that. Shall we move on to more on the practical side? So again, the area under a curve, the definite integral of a function fx, which lies above the x-axis, can be interpreted as the area under the curve of fx, or the function of x. Thus, the area shaded blue below is given by the definite integral, or the Newton-Leibniz formula. So you can find out this area here using this formula with your limits. So you find the integral of this function, and then you put in the upper limit, this value. Then you take away the lower limit. Okay. Let me give you some examples. Here's an example here. So here we have a straight line, and we're using the line if x is equal to x, or y is equal to x. Okay? That's the equation of that line. And we want to know what is the area under the line from 0 to 3. So, therefore, 3, the up one, this is b, the higher number, and the lower number 0. And fx is equal to x. Therefore, we can just put x dx. Okay, this is what we want to know. Now, first things first, what's our law for how do we integrate this? What's the integral of x? Okay, what we do is here, n plus 1, xn plus 1 over n plus 1. Therefore, the integral of x will be x2, and n plus 1 equals 2, x2 over 2. So we take that value. Okay, this is f. Remember f, don't forget again, f dash is equal to f. The derivative of capital F equals f. And when we integrate f, we get capital F. Therefore, f of b, and b was 3, take away f0. So we substitute the 3 in here, and then we take away 0 as well. Let's do that over here. Therefore, 3 squared over 2 minus 0 squared over 2. Okay. And what we get, 3 3s are 9, 9 divided by 2, 4.5 minus 0 over 2, 0. So the answer is 4.5. Now, look what we can do here. We can also use, what's the formula for the area of a triangle? See that triangle there? And you have 3 here and 3 there. Half the base times the height. Half of 3 equals 1.5 times 3 equals 4.5. Same answer, right? 4.5 is the area of a triangle, and 4.5 using our formula here for the definite integral. By the way, just briefly, that formula that we just did here is this formula right here. Okay? Okay, let's move on to another example. So our first example had a straight line, and now we have a curve. Instead of y equals x, now we're using y equals x squared. And here, the explanation is already given. So what we're looking for here is the area under the curve of S. Okay, we want to know this. What's the area there? So we take the 2 points on the x-axis. You have a 2 here and a 1 here. Therefore, when we integrate, when we find the integral of x squared equals xn plus 1 over n plus 1, the integral, therefore it's x3 over 3, right? That's the integral of that. Now the other way, just for your information, dash. If we're looking for the derivative of x squared, we go down, it becomes 2x. So it becomes 2x, x squared, and then this is a derivative and like that, and that's f dash here. And to integrate, we get x3 over 3. Now, to find the area, S, we take the 2 points, okay, 2 and 1, function of x dx, and that is equal to x squared. So x squared, you get f of 2 minus the f of 1. See how it's capital F? So we have the integral. Now we just put in the 2 here, and then we take away the same 1, putting in 1. So what that means is now 2 cubed over 3 minus 1 over 3, 2 to the 4th was 8 over 3, minus 1 over 3 over 3, which equals to 3 3s are 9, 7 over 3. Is that right? Which is 2.2 1/3. We did the long way. 3 3s are 9. 8 to 24. 1 to 3. 21 over 9. Divided by 3. 2 and 1/3, or 2 and 1 over 3, or 7 over 3. And therefore, so 2 over 3. So the area of S is 2.33 continuous. Okay, let's move on. So thank you everyone for joining our session today. And here's your homework. Try this at home. Evaluate the definite integral 2. Okay, notice the limits. The integral of 2 and 1. And the function of x is x squared minus x with respect to x. Next week we'll go through the answer. Thank you for viewing today's lesson again with Everyday Seminar. Have a good day.